Hello. Let's begin section 5.2. Let's continue integration. This is integration using log and exponential functions. So the integral of e to the x is e to the x plus c. So remember, the derivative of e to the x is e to the x. So the integral of e to the x is e to the x. The integral of e to the ax, where you have a number in front of x, okay, coefficient, is 1 over a e to the ax plus c. So let's do an example. So the first example we'll do is e to the 1/2 x, right? So the derivative, or a, is actually 1/2. 1 over a is 1 over 1/2, whoops, which is 1 over 1/2, which is 2. So then this whole thing becomes 2 e to the 1/2 x plus c. Okay. The good thing about integration is you can always do a check. So let's check this. Because remember, integration and derivation or derivatives are opposites of each other. So if you take the derivative of 2e to the 1/2 x plus c, and then you take the derivative, you should get your original function back that you wanted to integrate. So remember how we take the derivative, you leave the 2 alone. The derivative of e to the something is e to the something times the derivative of the inside. What's the derivative of 1/2 x? 1/2. The derivative of c is 0. 2 times 1/2 gives me 1, so I'm left with e to the 1/2 x. And that's what I had. Okay? That is applying the chain rule. So if you are never sure, you can always just check, okay, using the derivatives. Let's do another one. 6e to the minus 3x dx. Okay, so the dx tells you that you're taking the derivative with respect to x. So again, leave that 6 alone. Okay, and then it's 1 over a. So a here is -3, so the -3 will go on the bottom. E to the -3x plus c. So then that becomes -2 e to the -3x plus c. Okay. And then let's take the integral of e to the pi x dx. Okay. Now here a is pi, so that's 1 over a, so that's 1 over pi. Let me just write down my work in between, and you can always write it down, right? Put these intermediate steps in. A is pi, so 1 over a is 1 over pi. So then that's the formula I'm using here. 1 over pi e to the pi x plus c. Okay. Let's look at integral of 1 over x dx. Now you think, what is the derivative, or the derivative of what function is 1 over x? Well, we know that's natural log of x. And we write natural log of absolute value of x plus c. Okay. So the integral of 5 over 2x. I'm sorry. Over 2x dx. Okay. So we can break this up as 5 over 2 times 1 over x dx. Okay, remember the x is on the bottom. So anytime you have x on the bottom, then you have to use the natural log. Okay, so this is 5 over 2. Leave the constant multiple alone. Natural log of x plus c. Okay. Remember when we did last video, section 5.1, we had the rule that the integral of x to the n dx is x to the n plus 1, right? Add 1 to the exponent, divide by the new exponent. But as long as n is not equal to -1, right? So that's why, because when x is equal to -1, you get 1 over x. And the derivative, or the integral of 1 over x is natural log of x. Okay? So this was from before. Right here, review. Okay, so now you know the reason why we had that condition in there. Let's do another example. Integral of x to the -1 plus x to the -2 dx. Okay. So x to the -1 is 1 over x, so the derivative, or the integral of that, is natural log of x. X to the -2, now we have to do like we did before, right? Add 1 to the exponent, divide by the new exponent, which is -1, so then this becomes a minus x to the -1 plus c. And then let me just, you don't have to simplify this, right? The general rule of thumb is you leave it in the format of the original problem, but if you wanted to simplify, it would become this, and that would be your final answer. Okay. Number 6, the integral of 3 over 4x dx. Okay, again, leave that 3/4 alone, and then that's 1 over x, so that's natural log of x plus c. Okay. Let's look at an example in your book. So this is on page 340, example 5. Okay. So we have another, find an electronics dealer, and this one right here. He estimates that during month T of a sale, a discontinued computer will sell at a rate of approximately 25 over T per month, where T equals 1 corresponds to the beginning of the sale, at which time none have been sold. So find a formula for the total number of computers that will be sold up to month T. Will the store's inventory of 64 computers be sold by month 12? So let's look at the problem again. 25 over T, that's the rate, okay? And they give me the rate, and they want the find a formula for the total number of computers. So I am going from, oops, where's my mouse? Let's see. Sorry, page. So I am going from, so this is on page 340, example 5. So you are going from a rate to a total. So remember we looked at this last time. When you go from a rate to a total, you have to integrate. Okay, you need to take the integral. And the rate that they gave me was 25 over T. Okay. And they said find the total. Okay, so I'm going to integrate 25 over T dt. Okay, so again, this is the integral. I haven't taken the integral yet, I'm just rewriting it, so I need to include that integral sign. This is like 25 times 1 over T, isn't it? So we know we leave the 25 alone, and you do natural log of T. And then don't forget the plus C. Okay. Now we have to use the information they give us, because we need to solve for that T, or solve for that C, right? So they say T equals 1 corresponds to the beginning of the sale. Okay? So T equals 1 corresponds to the beginning of the sale. So let me call this capital F of T. Okay. So the beginning of the sale, T equals 1 corresponds to the beginning of the sale. So at the beginning of the sale, how many computers would have been sold? 0, right? So that means F of 1 equals 0 because 0 computers sold. So now I can do 25 natural log of 1, that's capital F of 1, plus C equals 0. Natural log of 1 is 0, so this part equals 0. So then when I solve this, I get C equals 0. So my actual function is 25 natural log of x. And I don't really need the absolute value there because we're dealing with time, and time is always positive. Okay, so 25 ln t. And then there was another part of the question. To find the number sold up to month 12. Oh, I'm sorry, that was the part of the question. Will the store's inventory of 64 computers be sold by month 12? So you want to know, by month 12, will they have 64 computers sold? So let's go back to that. So by month 12, so we need to find out what the total number of computers is by month 12. So you do 25 natural log of 12, okay? And that's going to give us some approximate value. Let me go to my calculator. So we have 25 natural log of 12. 62.1 roughly. Okay, so we're going to sell roughly 62 or 62.1 computers by month 12. So no 64 computers. 64 will not have been sold. Okay. Let's look at another example. This is on page 346 in your book. Okay. So example 6. Okay. This is finding a formula for the total consumption again. Now the annual world consumption of tin is predicted to be 0.26 e to the 0.01 t million metric tons per year, where t is the number of years since 2008. Find a formula for the total tin consumption. Estimate when the known world resources of 6.1 million metric tons will be exhausted. Okay. So let's do this and do this. Okay. So they told me, and this is on page 341 in your book. Okay, example 6. Oops. So 0.26, so that is the formula they give us. F of t equals 0.26 e to the 0.01 t. Okay. T is the number of years since 2008. Find a formula for the total tin consumption. So this is the rate they give us. And because how do we know it's a rate? It's metric tons per year, right? So sometimes even if they don't say the word rate, look at the units. The units will tell you that it's a rate, tons per year. So now we need to find the total consumption. So we're going to find the total, so we need to integrate. The integral of 0.26 e to the 0.01 t dt. Okay. Now remember, when we take the integral, we leave the 0.26 alone. And it's 1 over a. A here is 0.01, so that a goes on the bottom. Okay, let's do this. E to the 0.01 t plus c. Okay, and so when you do this, you can use your calculator. 0.26 divided by 0.01. Okay, you get 26. No surprise there, right? So my final answer is 26. Oops, where's the mouse? 26 e to the 0.01 t plus c. Now I need to solve for that c. We don't know. It says find the formula for the total consumption within 2 years of 2000 and estimate when the known world reserves of 6.1 million metric tons will be exhausted. Okay, so I can assume that at time beginning t equals 0, 2008, nothing has been used, right? So at time t equals 0, f of, so this is, let's call this capital F of t. We'll use capital F of t for the integrated formula, so for the total rather, so f of 0 is 0. Okay. Because nothing has been consumed yet. That's when our clock starts in 2008. Okay, that's how much reserves we have in 2008. So we're going to do f of 0 gives me 26 e to the 0.01 times 0 plus c, and that is 0. Okay, so I just applied this formula here. F of 0 equals 0. E to the 0 is 1, so we get 26 plus c equals 0. So then c equals negative 26. So now my formula is, oh Lord. Oops, I'm running out of space. So let me just write this here. So that is 26 e to the 0.01 t minus 26. Okay, that is my formula for the total consumption. Okay, and then estimate when the known world reserves of 6.1 million metric tons will be exhausted. Now check your units. The formula they gave me was in million metric tons. This is in million metric tons. So I just need to set my formula equal to 6.1. So this was the total. So I need to set this equal to 6.1. So 26 e to the 0.01 t minus 26 equals 6.1. Okay. Now how do I solve for this? First thing I'm going to do is add the 26 to both sides. Okay, then we get 26, right? E to the 0.01 t equals, what is that? 32.1. Okay. And then I'm going to divide both sides by 26. Now, the whole point is I'm trying to solve for t, right? I want to find out when will this much be consumed. So we do get the t by itself. Okay, so 0.01 t equals, and if I were you, I would not actually plug this into the calculator yet. Leave it like this, okay? Because we still have to do some more calculations, and if you round now, or if you get a decimal now, then round, and then you do some more computations on that, your rounding might be a little bit off, okay? Now, how do we get rid of the e? We have to take the natural log of both sides. Remember, natural log and e are inverses, right? They're opposite of each other. So then on the left side, we get 0.01 t, right? Natural log and e cancel each other out, and I'm left with natural log of 32.1 over 26. Okay, and then I want to divide by both sides by 0.01. This is being multiplied. Okay. So then we get t equals natural log of 32.1 divided by 26 divided by 0.01. Okay, let's plug that into the calculator. So we have, and I like to do this in pieces, so that way, so we get 32.1 divided by 26, enter, and then we're going to divide that by 0.01, enter, so we get 21.075, or 21.076. Years. So roughly, so very much after 21 years. 2008 was the beginning of the clock. So in 2008 plus 21 gives me roughly in 2029. Okay. In 2029, that many metric tons will be exhausted. 6.1 million metric tons will be exhausted. Okay, 6.1. So that is all of section 5.2. I want you to go through and do a bunch of practice problems. And if you have any questions, then please feel free to get in touch with me, okay? And then also work on your homework. All right, thank you for watching.